Here we have a question based on the concept of motion of a charged particle kept in a uniform external electric field. We are considering here two particles. One is electron, the other one is proton. Their masses are taken as ME and MP respectively. They both are initially at rest and released in a uniform external electric field region. It is said that they take different amounts of time, T1 and T2 respectively, to cover the same distance. We are supposed to find the ratio of T2 to T1, neglecting the effect of gravity. Here are the given options. Well, let's first understand the force experienced by a charged particle when it is kept in a uniform external electric field, capital E. If the charge on it is Q, the force on it will be written as Q into capital E. If it is a positively charged particle, the direction of this force will be along the direction of electric field itself. If it is a negatively charged particle, in direction this force will be opposite to that of the electric field applied. Now, let's consider the force on electron and proton. It can be written as Fe equals minus E capital E for the case of electron, and for the case of proton, Fp equals plus small e capital E. Why is there a minus sign? Because electron is negatively charged particle. In both the cases, electron and proton's cases, the charge happens to be in magnitude small e, but one is positive, one is negative. So, let's find the acceleration of electron and proton first. Acceleration of electron will be simply force divided by the mass. How do you get it? Newton's second law, of course. It will be small e, capital E, divided by the mass of electron. This is the magnitude. Now, that for proton will be small e, capital E, divided by the mass of proton. Do you notice that these two values are different? Now, let us look at the distance traveled by the electron and the proton and the time taken. This is how they travel. The proton will move along the direction of the electric field. Electron will move in a direction opposite to that of electric field. For the same distance, they take different amounts of time, T1 and T2. You can apply now the equation of motion S is equal to ut plus half at square, because in both the cases, acceleration remains constant. But in these cases, the acceleration are different in value, I agree. But these are constant in magnitude in each case. So, for electron, I can write S is equal to ut plus half at square. Ut is 0 because initial velocity given is 0. So, 0 plus half into acceleration of electron is small e, capital E by me into the time taken as T1. So, T1 square. Call this equation number 1. Now, that for proton will be S is equal to same way 0 plus half into E capital E divided by mass of proton into the time taken in this case is T2. So, T2 square. What do we need? The ratio of T2 to T1. So, if you take the ratio of these two equations, you get half small e capital E divided by MP T2 square divided by half small e capital E divided by ME T1 square equals 1. So, after cancelling these things, we get T2 square by T1 square to be MP by ME. We need T2 by T1. So, take the square root on both sides. You get T2 by T1 to be square root of MP by ME. This is the answer you need. Now, let's look at the options. The correct one happens to be B. Here is a question which combines motion in 2D concept that you learnt earlier with electrostatics. We are given here a charged particle of mass 1 kg and charge 2 microcoulomb. It is projected from the ground at an angle 45 degree with respect to horizontal. In this space, there is a horizontal electric field of magnitude 2 into 10 to the power 7 volt per meter in addition to the gravitational field. Now, we are asked to find the horizontal range of this projectile over the ground. You can take acceleration due to gravity to be 10 meter per second square, and here are our options in meter. Alright. Here is a charged particle. It is subjected to two forces. One force is due to the gravity and another force is due to the electric field to which it is subjected. Remember, we are looking at a positively charged particle, so the force acting on it will be along the direction of electric field itself. What is the equation governing the force and the electric field and the charge? F is equal to QE. We will use that later. But first let's understand what is happening here. How does a charged particle move? It is subjected to two forces. One is gravity in the downward direction. Another is the force due to electric field towards right. This is how it will move. Well, if there was no electric field at all, it would be a simple case of projectile motion. It goes up, moves along the parabolic path and comes down. What is the effect of the addition of electric field in this situation? Simple. The motion of this charged particle will be affected by the electric field's presence because now there is an acceleration along the x-axis. The velocity along the x-axis will not remain a constant. The range over the ground will increase. In order to find this range, let's call it capital R. Let's look at the application of equations of motion. Well, along the x-axis, you can take x is equal to uxt plus half ax t square. And along the y-axis, you can take y is equal to uyt plus half ay t square. The initial velocity u can be resolved into two perpendicular components. Taking this as x-axis and this as y-axis, you can take u, which is 20 meter per second in magnitude, and resolve it into ux, which is 20 cos 45 degree, because this is 45 degree. How much is it? 20 into 1 by root 2 meter per second. And uy, the component along y-axis, turns out to be 20 by root 2 meter per second as well. How do we go about finding the range? Simple. We will use this equation. Do we know ux? Yes. Do we know ax? Can be found out. How? Simple. We know the force that the charged particle experiences due to the electric field's presence. And we can find out acceleration along x-axis. But do we know the total time taken by the charged particle to reach the ground again? Or, in other words, the total time of flight? Not yet. So let's find that out first. In order to find the time of flight, we will look at the motion along the y-axis. Why? Simple. There is only one force acting along the y-axis, gravity. And we know that using this equation, we can find the time of flight. That's because in the beginning and at the end of the projectile motion, y displacement happens to be 0. So, since it comes back to ground, y is 0 at the end of the motion, and this will give us 0 equals uy. What is uy? 20 by root 2. Let's take the total time of flight to be capital T plus half ay. Ay is the acceleration due to gravity, which is in the downward direction. So, with our sign convention, Let's take that to be minus g and then time of flight t square. Simplify this and you get t to be 40 divided by 2 divided by 10. This will give us 2 root 2 second. So now we have the total time of flight. It is 2 root 2 second. How do we find horizontal range from this information? We need to apply this equation, right? And before doing that, let's evaluate AX as well, because that's the only thing missing now. If you look at the force acting along x-axis and call it Fx, it happens to be QE. And in magnitude, Fx turns out to be Q into E. How much is Q? 2 microcoulomb. How much is E? 2 into 10 to the power 7 volt per meter. If you simplify this, you get 40 Newton. So that's the force acting along x-axis. Now, let's apply Newton's second law and find the acceleration along the x-axis. How much is it? Ax is Fx by m. Fx is 40 Newton. M is simply 1 kg. So Ax turns out to be 40 meter per second square. All right. Now we have everything we need in order to find out the range, capital R. At the end of the projectile motion, the x displacement happens to be equal to R. So applying this equation, we can write x is equal to R, and on the right hand side, Ux is 20 by root 2. T is 2 root 2 plus half into how much is Ax? It is 40 meter per second square, and T is 2 root 2. Square it. Let's simplify this. Root 2 and root 2 will get cancelled. This will turn out to be 40 meter plus this will be 20 into 2 root 2 whole square will give you 8. So simplifying this, we get 40 plus 160 or 200 meter. That's the horizontal range of this particle over the ground. Now, let's look at the options. The correct option is D, 200 meter. Let me help you with the data given here. We are considering a sample of HCl gas kept in a uniform electric field region. It is also said that each HCl molecule has got an electric dipole moment equal to 3.4 into 10 to the power minus 30 coulomb meter. We also have the magnitude of the electric field as well. We need to find the maximum torque that can act on a molecule under these circumstances. Here are our options. All right. Before proceeding with the calculation of the maximum torque acting on the dipole kept in a uniform electric field region, let's first understand what is this electric dipole all about and what is electric dipole moment. An electric dipole is a setup of two charges equal in magnitude, opposite in nature, and separated by a very small distance from each other. We associate a vector quantity with this electric dipole called dipole moment vector. We write it as P vector, and in magnitude it is equal to the magnitude of charge on either of the particles into the separation distance, let's say 2L between them. What about its direction? Simple. Electric dipole moment's direction is taken from negative charge to positive charge of the dipole. In other words, along the line from negative charge toward positive charge of the electric dipole. Why do we need this? Because it comes in handy in expressing the electric field created by this dipole itself in terms of dipole moment vector. Now, we are considering an electric dipole like this, a HCl molecule kept in a uniform electric field region. What is the magnitude of the electric field? The external electric field, capital E. If you look at the torque acting on the electric dipole, it happens to be tau equals P cross E. What is P here? Electric dipole moment vector. And vector E is external uniform electric field applied. Tau is the torque acting on the electric dipole. In magnitude, you can write it as tau equals P E sine theta. What is sine theta here? The angle between the electric dipole moment vector and the external electric field vector. When is this quantity a maximum? That's the question, isn't it? In fact, it becomes maximum when sine theta becomes maximum, and the maximum value of sine theta is 1. So, tau max, the maximum torque acting on the electric dipole, happens to be P into E. Do we have the values of P and E? Yes, we do. So, let's just substitute. Tau max happens to be P, which is 3.4 into 10 to the power minus 30 into 2.5 into 10 to the power 4 Newton meter. If you simplify this, you get the maximum torque acting on the electric dipole under the given circumstances to be around 8.5 into 10 to the power minus 26 Newton meter. That's your final answer. Now, let's look at the options. Obviously, the correct option is C. Let's look at the next question. We are given here two charges, plus 5 coulomb and minus 5 coulomb, kept at end points of hypotenuse of a right angle triangle as shown. What do we need to find? The electric dipole moment due to these two charges. And here are the given options. Alright. Let's find the electric dipole moment vector's magnitude and direction both. But first, let's understand what is electric dipole and its dipole moment vector all about. What is an electric dipole? It's basically a setup of two charges equal in magnitude but opposite in nature and separated by a very small distance. We also associate a vector quantity called electric dipole moment vector with this dipole because it becomes easy for us to express the electric field created by this dipole in terms of the electric dipole moment vector itself. What is the magnitude of such electric dipole moment vector? Simple. It can be written as P equals Q into 2L. P is the magnitude of the electric dipole moment vector. Q is the magnitude of either of the charges. Remember, magnitude. 2L is the separation distance between the two charges given. What about the direction of the electric dipole moment vector? Simple. It is along the line joining these two charges and in direction from negative charge towards positive charge. So, here is minus 5 coulomb, here is plus 5 coulomb. Obviously, vector P will be in this direction. Now that we have found out the direction of the electric dipole moment vector, let's find its magnitude. P is equal to the magnitude of the charge on either of these particles will be 5 coulomb into the distance of separation between them. Well, this is a right angle triangle and we are looking at the hypotenuse. These two sides are 3 meter and 4 meter respectively. Obviously, this hypotenuse has to be in length 5 meter. So, the final electric dipole moment vector in magnitude turns out to be 25 coulomb meter. This is your final answer. And we already know the direction. It's along CB. Now, let's look at the options. The correct one happens to be D. The next question we have here is on the concept of electric field and electric field lines. We are given 2 point charges Q and minus Q, which are said to be fixed at two locations. The coordinates are minus a comma 0 and plus a comma 0 respectively. Look at the options. They have to do with determining of the direction of electric field at a given point on x-axis or y-axis. All right. Here are the two charges from data. This is y-axis. This is supposed to be x-axis, and here is your origin. Before I draw the field lines around these charges and tell you the direction of electric field at a given point on x-axis or y-axis, let me give you a quick recap of the electric field line concept. What is electric field line? It's an imaginary line that we draw around a charge which gives us information on, an idea on the magnitude of electric field there and the direction as well. We have certain norms. In this model, we consider the field lines to emerge from positive charge and end up at negative charge. Also, the field lines should not intersect. Why? If you draw the tangent at a point on the field line, it gives us the direction of electric field in this model. If two field lines intersect, it means that there are two directions for the electric field there, which is absurd, right? Also, we say that relatively denser the field lines are in a certain region, the more intense the field is in that location. There is one more norm that we follow. The more the magnitude of the charge, the more the field lines associated with that charge. For example, if you have plus 4 millicoulomb charge somewhere, and if you decide to draw 100 field lines emerging from that plus 4 millicoulomb charge, then at a location, if you have minus 3 millicoulomb charge, you have to draw 75 field lines ending up on that minus 3 millicoulomb charge. All right. With all this information in mind, let's look at how the field lines look like around these two charges. Here they are. They emerge from positive charge and end up at negative charge. Look at the charges. They're equal in magnitude. Exactly why the number of field lines around plus q is as good as the number of field lines around minus q. Now, look at the direction of the field. In the region number 1, the direction of the field is along negative x-axis. In region number 2, at a point on x-axis, the field is along positive x-axis. And in region number 3, at a point on x-axis, the field is along negative x-axis. So we can conclude that along the x-axis, the field doesn't remain same in direction. It changes from point to point. All right. Now let's take a point on y-axis. Do you see that at any point you choose on the y-axis, the field is simply along positive x-axis? Well, with all these deductions, let's look at the options given once again. Obviously, the correct option is B. E at all points, the direction of electric field at all points on the y-axis is simply along positive x-axis or along I cap, the unit vector that we choose along positive x-axis.